Hello, in this video, we are going to take a look at a couple examples using the direct comparison test. So for this first example, we have the sum from k equals 3 to infinity of the natural log of k over k. First step, basic step, is to just say, is this positive? Yes. ln k over k is definitely positive for those terms, because ln k is greater than 0 when k is greater than 1. Well, yeah, k is greater than 1. So our series is positive. Great. Now we want to find something to compare it to. So we have the natural log of k over k, and we want to compare it to some series. Most often, we want to compare to a geometric or a p series. The easiest p series to see is the thing that's throwing me off is this natural log of k. What if I just get rid of it? So the easiest p series to compare to would be 1 over k. So that's exactly what we're going to compare it to. We're going to compare to the series k equals 3 to infinity of 1 over k. Does the series converge or diverge? This diverges because it's a p series with p equal 1. It also has a very special name, and that is the harmonic. So this diverges because it is the harmonic series. So we have what we want to compare to. We know what we want to compare to diverges. Now for the direct comparison test, we just need to know how do the sequences of what we're comparing compare to each other. So the natural log of k equals 1 at e. So natural log of e equals 1. However, e is smaller than 3. So that means the natural log of k, when k is bigger than 3, is bigger than 1. So natural log of k over k is bigger than 1 over k. Because natural log of k is bigger than 1 for k bigger than or equal to 3. So we've run our test. We know for a fact the natural log of k over k is bigger than 1 over k. We have what we're comparing to. We ran our test. And going back to our test, what we're comparing to diverges, and the sequence an is bigger than the sequence bn. So we have an, we have bn, and we have that the series of bn diverges. That means the series k equals 3 to infinity of the natural log of k over k diverges by the direct comparison test, since the series k equals 3 to infinity 1 over k diverges. Now, we want to look at one more example. And that is this example of the series n equals 1 to infinity 2 plus sine squared n over n to the 5th. In this problem, there's a few little things we have to watch out for because there's actually multiple series we can compare to, but we need to pick the exact right one. So I'm gonna look at the sine squared n part after we do that first step. And that's just checking in our mind, is this always positive? Yes. 2 plus sine squared n over n to the fifth is bigger than 0 when n is bigger than or equal to 1. Because, as we're just about to get into, we're looking at that sine squared n piece. And sine squared n is the only thing that could have been making this negative anywhere, is n to the fifth, always positive when n is positive. 2, definitely always positive, it's just 2. So it's that sine squared n piece. However, because we're squaring sine squared n is positive. So it's never going to be smaller than 0. Sine squared n also can never be bigger than 1, because the biggest sine can be is 1, and 1 squared is 1. So the biggest sine squared can ever be is 1. That means if I add on 2 and divide by 5, 2 plus 0 is 0 over n to the fifth is less than or equal to plus sine squared n over n to the fifth, which is less than or equal to 1 plus 2, which is 3 over n to the fifth. And so we have two series we could be comparing to. We could be comparing to 2 over n to the fifth series, or we could be comparing to 3 over n to the fifth series. However, I'm just going to look at the over n to the fifth part to help us figure out which one we want to pick. So we're comparing to a series. It is either 2 over n to the fifth or 3 over n to the fifth. And this is going to be a p series with p equal to 5. So this is going to converge whether this numerator is 2 or 3. P equal to 5, which is greater than 1. And so we now need to essentially run our test, which is determining which series we actually want to use. So going back up to the rules for the direct comparison test, the direct comparison test says if an is smaller than bn and bn converges, then so does the series an. And if an is bigger than bn and bn diverges, then so does the series of an. We have a case where what we're comparing to converges. So we really want to use this first line. And the first line says we need the sequence an to be smaller than the sequence bn. So going back, an is the series we want to know about, or the sequence for the series we want to know about. We're comparing to the series of bn. And we want an, because we're comparing to a convergent series, we want an to be smaller than bn. That means there's only one part of this inequality that helps us. the 2 plus sine squared n over n to the fifth. That part of the inequality being less than or equal to 3 over n to the fifth says, since we're looking at a convergent series, we want an to be smaller than the convergent series. So we want the 3 over n to the fifth series. So that is what we're going to compare to. And in that case, we have just run our test because we figured out this is the part of my inequality I want. So we can now make that conclusion. We have the part of the inequality we want. We have the series n equals 1 to infinity of 3 over n to the fifth converging by p-series test. This means the series we're looking at, 2 plus sine squared n over n to the fifth, converges by the direct comparison test, since the series n equals 1 to infinity of 3 over n to the fifth converges. So there are a couple examples of the direct comparison test. However, let's make a couple of notes. There are a couple notes about the comparison test that are important to pay attention to. And these are the same notes we made about the integral comparison test. And that is, if we have the inequalities essentially backwards, say the small that an is smaller than bn, and we know the series of bn diverges. So the big thing diverges. Or we have an bigger than bn, and so now bn is the small thing, and the small thing converges. If we have these two cases, these are the two cases that weren't in the comparison test list. If we have these cases, we don't know what the series an does. Meaning the direct comparison test does not work. So the direct comparison test, it's great when we get these inequalities nicely and the appropriate series is converging or diverging. But when this wording doesn't line up, we can't use it. It just does not work. So this is where we're going to introduce a new test in the next video known as the limit comparison test. And the limit comparison test will solve this problem of what if I have the reverse inequality of what I want. So next video, we will look at the limit comparison test.